The topic of this problem is series and parallel independent sources. In this problem, we want to determine the current I3 and the voltage associated with the node which has been designated as node 1, which is the node at the top of the circuit. And so to do this, the first thing we're going to do is we're going to start combining some of our elements. We see that, first of all, that we have a parallel combination of several elements in this circuit. But in particular, we have a parallel combination of current sources. We have a 4 amp current source on the right-hand side of the circuit, which is a downward current source, and we have a 6 amp current source on the right-hand side, which is an upward current source. So we can just think of those, first of all, as two sources which are in parallel with one another, two current sources. So they look kind of like this if we redraw just those two components of our circuit. We have a 6 amp upwards, 4 amp downward, and ultimately what we would end up in this case is we'd end up with 2 amps from the combination of those two sources. So we're going to redraw our circuit with those two sources combined with each other, and there's our 2 amp source from doing that. We also notice that we have these resistors that are a resistor network on the right-hand side of our circuit. We have two 6 ohm resistors in parallel, and they're in series with a 15 ohm source. So if we start with the two 6 ohm resistors that we have, we see that the combination of those two 6 ohm resistors, 6 in parallel with 6, is going to equal 3 ohms. That gives us a 3 ohm resistance from the combination of those two resistors in parallel. We also know that those two resistors, which are in parallel, are in series with a 15 ohm. So we have a 15 ohm plus a 3 ohm, and that gives us 18 ohms equivalent for those two, or those 3 resistors in series and parallel. And so we're going to redraw a circuit with those resistors, but we're going to take it one step further. We're going to take those resistors, which combine to be 18 ohms, and we're going to also notice that they are in parallel with the 9 ohm resistor. So we have an 18 ohm resistor in parallel with a 9 ohm resistor. The parallel combination of the 18 ohm resistor and the 9 ohm resistor gives us a 6 ohm equivalent resistance. And so we're going to redraw our circuit with those changes to our circuit. So we still have our 3 ohm resistor, and the reason we didn't combine that with our other resistors is because we're looking for the current through that resistance. So we don't want to combine it and lose our ability to solve for I3 by doing so. So we're going to take those different elements that we have left after we do our combination of resistors, and we've already done our combination of current sources. We're going to leave our current-controlled current source intact. It's a 0.9 I3 going upward. And we also have then our combined resistances left, which is a 6 ohm resistance. So that's our redrawn circuit. Now it's a little bit easier for us to go back and to write our nodal equation for node 1 at the top of our circuit. So we're going to use Kirchhoff's current law to solve this circuit, since it's now a 2-node circuit, a node at the top and our ground node at the bottom of the circuit. And Kirchhoff's current law can be used either by combining the currents that are flowing into a node, or complementary, you can combine the currents out of that node. So in this problem, we're going to combine the currents, or add the currents, that are flowing into the top node. First of all, we know that we have a 2 amp source, which is flowing into the node. We have I3, which is flowing out of the node. We have 0.9 I3 flowing into the node. And we also have the current, which is going down through the 6 ohm resistor on the right-hand side of the circuit. And that current we know is going to be equal to, and it's flowing out of the top node, so we're going to put a negative sign. It's going to be equal to V sub 1, which is the voltage associated with the top node, divided by 6 ohms, using Ohm's law, and that's equal to 0. So we've used Kirchhoff's current law, which is the sum of the currents into any node equals 0 at any instant in time, to come up with our first equation. So that's equation number 1. So we notice that equation number 1 has two unknowns. It has an unknown I sub 3 and it has a V sub 1. So we need another independent equation so that we'll have two equations along with our two unknowns to solve this circuit. So to do this, we notice that we have a relationship between the nodal voltage and I sub 3 through the 3 ohm resistor. We know using Ohm's law that V sub 1 is equal to I sub 3 times the 3 ohms. So that gives us a second equation, which is independent from our first equation. V1 is equal to I sub 3 times 3. Now we have two equations and two unknowns. So if we use matrix analysis or elimination of the variables, however you want to solve the circuit, we find I sub 3 is equal to 2 divided by 0.6 amps. And once we know I sub 3, we can find V sub 1 using our equation 2 that we've already come up with. So we know that V sub 1 using Ohm's law is equal to 2 divided by 0.6 amps times 3 ohms, and so that gives us 10 volts for V sub 1.